Welcome to Walkabout the Galaxy, the viral astronomy podcast, where the science is universal, the opinions are personal, and the topics are unpredictable. We are Strange, Charm, and Top the Astroquarks, also known as Josh Cole, Addie Dove, and Jim Cooney, coming to you from the Walkabout studios at the University of Central Florida. Today we're happy to welcome special guest Dr. Renee Weber, manager of the Heliophysics and Planetary Science Division at NASA's Marshall Space Flight Center. Did I get that right?
That's me.
And a member of the Mars Insight mission.
Correct.
Welcome to the show.
Thank you.
Great to have you. Show your support for Walkabout the Galaxy with our stylish new Walkabout the Galaxy t-shirts available from walkaboutthegalaxy.com, or write us a review wherever you get your podcasts.
They are very good.
They're pretty nice.
Excellent.
So do you also ask people to subscribe to your channel?
Yeah.
We do.
Subscribe to this channel.
We do. we ask them that at the end of the show.
Oh, okay.
Yeah.
I jumped the gun a little bit.
Is the spoiler alert.
Spoiler alert. We would like you to subscribe.
Yeah. Our stumpers today are philosophical. I'm sorry, philosopherical.
Okay.
Is that better?
No.
Philosophical.
Philosophical. Jim, Descartes or Sartre?
So I'll admit that I am fairly ignorant about philosophy in general, though I did take a really awesome philosophy of science course when I was in college. I thought that was great. But I definitely go with Descartes here.
Because of Cartesian?
Because, yeah. Cartesian. Because, yeah, he was, I think, my vague understanding is he did a lot of sciencey stuff. He was, the Cartesian coordinate system is named for him. He did a lot of stuff in algebra and geometry that led to the kind of underpinnings of calculus, which came a little bit after. So that was pretty great. Sartre, I think, was more just...
He was just one of the...
Just a writer and
standard depressed philosopher.
Right.
Yeah.
And I think some of his stuff is pretty cool, but I don't understand it. So I have to go with... not that I understand Descartes.
Was it Sartre or Camus who wrote the play No Exit, where a bunch of people are in hell, but they don't know that that's where they are, but it turns out hell is just other people?
Oh,
It's
yeah.
just like being in a room with other people.
Yeah,
That's like
just
that
the
TV
hell.
just the show, The Good
The
Place.
Good Place.
Yeah, I thought that might have resonated with you, Jim.
No, I do hate people, but except you guys, you're great, and all of our listeners. So yeah, Descartes.
Okay, Addie, Kant or Nietzsche?
I also am not well philosophically trained. But I'm going to go with Kant.
Also, because he was sort of
He was more
astrophysically
sciencey and
inclined.
astrophysically than Nietzsche.
Right. Who was also another one of these sort of everything is terrible philosophers.
Yeah, he was less into like science is an interesting thing, and I think Kant was more on the lines of sort of logical thought and thinking about how science actually works, and actually did a little bit in the realm of science.
Yeah. Renee, I got one for you. Now you've seen how these things work.
Mm-hmm.
Okay, you ready?
Yeah.
Yoda or Data?
Ooh.
Oh man, that's a good one.
Ooh, that's hard. I'm going to go with Data.
Yes.
Okay.
Yeah.
Nice.
Big
Good call.
big fan of Star Trek. So,
Right. Yeah. Good.
Was that your favorite Star Trek, The Next Generation?
Of course.
Okay,
Excellent.
good call.
Is that also your favorite?
Oh yeah, well, we grew up.
You grew
Favorite
up.
of mine.
I think,
it
yeah,
was.
we grew up at that time. Yeah.
Thank you for reminding me how old I am.
Yeah.
Well, today we'll talk about insights into Mars with Renee, polluted white dwarfs as well. But first, this episode of Walkabout the Galaxy is brought to you by heliocentric models.
Nice.
Attractive,
My favorite kind.
attractive, practical, and ready to display all heavenly bodies just as they should be seen. Choose heliocentric models for your next show. Heliocentric models combines the homey comfort of geocentric models with the excitement of whirling around the sun at 30 kilometers per second. As a bonus, heliocentric models brings you apparent retrograde motion, accurate eclipse predictions, and the correct scale of the solar system. Don't try to stretch your new outfit. Just call heliocentric models, guaranteed to fit your observations perfectly. Heliocentric models. Have it your way. Space news. The big space news today, the day we're recording this, October 18th.
Spacewalk.
The
yes.
spacewalk we mentioned on our last episode happened today.
Yay.
Fantastic.
Finally.
How'd it go?
It went well.
How long were they out?
They were actually out for a pretty long time. I didn't see the final number.
It was scheduled to be about 5.5 hours, I think. So
It was a 7-hour and 17-minute spacewalk.
Wow.
Fantastic.
They spent a long time.
Yeah.
You had to
And
drag,
they
you had to
had
drag
to-
that one out.
Yeah, I know, right? They replaced a failed power controller and completed several other tasks in prep for future spacewalks.
Did they, space high five?
They did a bunch. They did a bunch of cool, like, oh hey, that's a place, and they were talking about things they were passing over a few times when they were like
On the
pausing in
Earth
between.
or on the space
Yeah, when
station?
they were passing over things on Earth, they were
They're
like, oh
like-
hey, San Diego.
Oh, okay.
And I think they probably did some cool high fives. I haven't seen all the pictures yet.
Okay.
So
What- go
I'm
ahead.
an idiot about the space exploration and
Yes.
flight.
That's why we have you on this show, Jim.
Yeah. No. I know a lot of physics and astronomy, but very little about rockets.
Uh-huh.
Do
There were
they?
no rockets involved in the spacewalk today.
Right.
Okay.
Do they have mini rockets? Don't they have little?
They do.
My
don't.
question is,
I don't think
do they
so.
not?
They do not.
Okay.
No, they
so
don't have,
they're all tethered.
they're all tethered.
They're
Yep.
tethered. Do they carry the little spray can, the safer unit?
They
There
might
used to
have a
be a thing
safer
where they have
on
a-
their unit that's
they
like
have a
an
spray
emergency thing.
that they can spray
They can like
if they get
vector themselves
back. Yeah.
Yeah. Was that your question?
Yeah, that was my
Okay.
question. Because in the beginning they all had tethers, and then they did a few where they were not
The
tethered but had
EMU.
little rocket pack things on them.
The EMU.
MMU.
Well, it had different names, but
Okay.
yeah.
Yeah. So I was wondering where we were
Now it would
at
have
today.
to be it couldn't be the
The
MMU anymore because
CMU.
that was the manned maneuvering
That's
unit.
right. Have to be
we
the
don't use that
PMU.
language anymore.
We don't use that language.
The Homo sapiens maneuvering unit.
Yeah, there we go.
Um,
Yeah, no, because most of the stuff they do is on station. They just move and tether. Occasionally, they like strap themselves onto the end of the arm, and the arm moves them.
Right.
Oh, cool.
Oh.
I don't think that's happened in a while though.
That's
I
like
know-
Insight.
They
yeah,
would-
exactly.
They would do that with shuttle. They would be some. I remember seeing some people
Yeah.
out on the end of the Canadarm of
Yeah.
the space shuttle. That'd be
Canadarm
pretty cool.
2 is on space station. Did Canada build the arm on Insight?
No.
Oh,
The arm on Insight is a flight spare from Phoenix lander.
Oh,
okay.
One
Canada
of-
builds most of the arms.
one of the things that
Well, maybe they.
I
No,
think
I
they
don't
might
think.
have.
Did
Yeah.
they build
I'll
it?
check.
Why don't you Google?
Okay.
one of the things that we don't realize, or I don't know, maybe I don't realize, maybe you all do, with spacewalking is like, oh, everything's weightless, so it's really easy. You just pick this up and move it around here. But it still requires a force
Right.
to
Right.
move a
Things
giant
in space
mass.
aren't
Right.
massless.
They're
They're
not
just
massless.
weightless.
Yeah,
Right.
so you don't need to do anything to pick it up. You can just hold it there. But if you want to move it, that's hard work.
Yeah.
Mhm.
So
Put in
you're
a
out there moving yourself around.
instrument to
It's
pound
hard
on.
work to move around and move that equipment around that you're dealing with. Let's see. So speaking of space walking, and that the backstory with the first all-female spacewalk was the spacesuit issue. And their spacesuits were in the news a lot this week.
There were.
Yeah.
Both NASA and Virgin Galactic revealed their new
Right.
spacesuits, and
Yes.
they're quite different.
Yes.
But they're also for different purposes.
You know who they should have had show off those new spacesuits?
Addie.
Heliocentric models.
No, they did technically.
Some
We're,
way.
We're all a little
We're
heliocentric.
all heliocentric models.
Yeah.
So yeah, the new moon suit
Or me.
was illustrated or demoed or introduced by NASA, and
Very
then-
America.
Yeah, it's red, white, and blue, right?
Yep.
I have not
And
seen these.
The
Very exciting.
Virgin Galactic, of course, those trips are just like you're in Spaceship Two and you're going for a ride. You're not going out into space. You don't need a pressure suit, but
Right.
they decided for your $250,000 ticket to space,
You need a cool.
you get a free tunic.
jumpsuit.
Yeah. I mean, when you fly with 0G, you get a nice little like flight suit.
Right. Yeah. Yeah.
So it makes sense.
And so they're
they
going to
worked
get
with Under Armour
You're
to
right.
design their suit.
right.
So now the question is, will the U.S. ski team adopt a derivative version of the spacesuit for their next
Oh.
competition?
why the ski team in particular?
So they didn't. I don't remember if it was for like a national competition, if it was for the Olympics or something. But they had uniforms that were sort of like space themed,
Oh.
or maybe they said NASA on them or something
Oh,
like
that's
that.
fun.
And I really wanted to get my hands on some of that stuff, but it was too hard to find.
Makes
Interesting.
sense.
Yeah.
That'd be fun. They could do maybe they'll do the Virgin Galactic version. It's made by Under Armour, so it would be like
Yeah, can I get like is there going to be one in for sale at Target that I can just like wear around the house?
probably not Target, but I'm sure you can pay many $100s and get one from.
I wonder if Virgin Galactic they'll probably make it so that you cannot get their spacesuit unless you
Yeah.
fly it. So that's
pay.
like part of the show-off aspect of it is that, yeah, that's my
Probably a better way to go
astronaut
is
suit.
just get yourself a pile of Walkabout the Galaxy
T-shirts.
Yes.
Where's
Yes.
my T-shirt?
Yeah. Yeah.
We'll
Are
have it
you
on
going to
order.
shoot it out of a cannon at me?
Yes, we'll shoot it out of a T-shirt cannon at you.
Do I have to go stand in the fountain on this quad?
You do. Yep. Yeah. Today here at UCF was Spirit Splash, which is a homecoming tradition for UCF, which is bunch of students run into
Running
the
into
reflecting
the
pond.
fountain.
It's a fountain.
As the last space news item I've got is sort of a peek ahead at trivia.
Okay.
SpaceX, as you know, we've talked about before, they launched 62 of their Starlink internet
Oh, yeah.
communication satellites. They've got another 60
I saw those.
queued up and ready to go.
Oh, yeah,
right?
you
I
actually
saw
saw them in the
those.
sky.
I saw them in the sky.
Oh, cool.
It was incredible. There was
the line of
them.
lights going
yeah,
across.
there's an app that will, or a website where you go, you put in your location, and it'll tell you go out and look at this place in the sky at this time.
Right.
It was very cool.
Cool.
It was very Star Trek futuristic.
That's neat.
Whoa.
And-
So
Not
you're
something
on
that
board
you-
with them.
Well, I don't know about
yeah,
Okay.
so that's
It was
60.
very cool to see. I'll just leave it at that.
Mhm.
That's 60. They've got another 60 that's poised on a rocket that's ready to go any day now, I think. And they say that they'll be sort of economically viable with 1,000. Their initial plan was 12,000, but apparently they just filed some paperwork for bandwidth to have up to 42,000
I think I saw
of
that.
these
gosh.
internet satellites. And you saw 60.
Yeah.
So multiply that by
And it was-
1,000.
It was
But really,
so
you only
roughly.
saw like
cool.
20 something probably.
Yeah, I mean, it was pretty dim.
Nevertheless,
But yeah.
there's
Yeah.
a lot of concerns looking ahead about what this will mean for ground-based astronomy,
Mm-hmm.
because they're not the only company that's talking about that kind of thing.
Yeah.
Cool. Let's talk about Mars.
Yay.
All right.
Mars.
Question.
Yes.
Does Mars have water?
Yes, it does.
What?
Crazy.
Just kidding. That's not what we're going to talk
Does
about
it-
today.
So maybe first remind everyone what InSight is. So you work on InSight.
hmm
What is this thing?
So
I
InSight
forget all the
is
time.
a geophysical monitoring station, and it is a lander. So it's not a rover. It doesn't drive around. It sits in one spot. It has instruments that it used the robotic arm to deploy down to the surface to monitor the planet for quakes, not earthquakes, but Mars quakes.
Mars quakes. Awesome.
It'd be hard to monitor for earthquakes.
Yeah,
And,
from Mars. Yeah.
To measure the heat flux out of the planet. So the idea is to essentially constrain the internal structure of the planet, the part that you can't see from orbit.
And the heat flux is due to residual heat from early formation of Mars that's still
Yes.
probably in the core but is slowly seeping out.
Yes,
But we don't really have any idea of like what rate it's seeping out or
not yet.
not yet. But soon,
Hopefully,
hopefully.
the
Fingers
mole,
crossed for
mole
the
is
mole.
on the move.
It is again.
Right. Yeah. So we've talked on previous episodes about this thing getting stuck, and we were maliciously
We were pretty mean about it.
sniggering about that failure because
It's
we've
the mole's fault.
well
no,
we,
it's the engineers who designed it.
we've had
No, it's
I know.
it's Mars.
It's Mars.
right.
Space is hard.
Mars is a fickle friend.
We've had our own hair-rending, teeth-gnashing experiences with dust clogging things up, and
Yes.
so it was a little bit of misery loves company, probably.
Mhm.
But as you were saying, that mole is now on the move. It's aiming to get quite deep into the interior,
Yes, up to 5 meters.
and right now it's about 5 inches or so.
Yeah.
So it's got a ways to
still,
go.
There's still
But
a
it's
little,
farther.
a little teeny part of it actually still sticking out.
Okay.
But yeah, originally, so when the mole is uses a self-hammering mechanism to essentially propel itself down, and it encountered an obstacle. In fact, before it had even fully left the support structure that was used to deploy it. And at first we thought, it must have hit a rock, which in and of itself is not necessarily like an end to the mole, because the way that it works, it can actually hammer itself around subsurface
That's pretty cool.
obstacles.
So it's not like a long, rigid 5 meter long
No,
drill.
it's maybe about a foot long, and
It's on a cable.
It's on a cable, a tether that's connected to the lander, and basically what happened was because it encountered this obstacle before it had been fully out of the support structure, it started trying to hammer around it, right? So basically it starts vertical, and if it encounters something, it can just essentially
starts turning an
and then it goes
angle.
around, right? So it started turning at an angle, and it got wedged inside the support structure. And so the first step in mitigation was to just remove the support structure so that they could see what was going on. Because while it was still inside, like there is a little window on the side of the support structure, but just the way the cameras are positioned, it was really hard to see what was happening inside. So they removed the support structure, and then you could see there was this little hole that looked, sort of like a cup or something, where it had walls, and there was the mole sticking out of it like a drinking straw, kind of tilted to the side like that. And basically, the hole itself was bigger than the diameter of the mole, maybe just because the mole had been like jostling around while it was trying to hammer itself free. And so the first mitigation step after they took the support structure off so that they could diagnose what was going on, the idea then became, all right, well, it should still work now that we've removed the thing that it was stuck on. However, there was not enough friction on the hull of the mole, because like the walls of this hole that it had created were not like in contact
They're
with
too
the
big.
mole,
Right.
So there needs to be friction.
So without that, it's just going to basically be like a pogo
Just
stick.
kind of pogo
and just sort of
stick,
hop
right.
up and down instead of pulling itself into the interior of the planet.
So the first step to try to mitigate that was to actually use the scoop on the end of the arm, to press on the soil with the hopes that it would like collapse the hole enough that there would be friction.
So it's a separate robotic arm on the InSight lander
Yeah.
that could reach out to that location and try to help it
Right.
maneuver its way in.
So that in and of itself is a little like soil cohesion experiment. So you can press on the soil and you can see like what happens as a result of however much force that you apply. But unfortunately did not work to collapse the walls of the hole. So the second mitigation step was to actually use the scoop to just pin the mole. So they used the scoop to provide force against the hull of the mole so that there was something that it could sort of recoil against, and that worked.
Right.
And that's why it's actually now successfully hammering down, and there's like animated GIFs of it,
Cool.
which you can find on
We'll
share.
social
It's a
media.
beautiful illustration of Newton's third law. It's like you can't push into something unless you've got something to push against.
Right.
Right.
And so when we dig a hole, the thing that is pushing, you push the shovel down, the shovel's pushing up on you, but your weight
Right.
is pushing back down on it, and this thing doesn't have that, so it needs the friction of the dirt around it, or now this
Right.
little robotic
Right.
scooper. To
So what's the prognosis? It should successfully be able to continue on now and get all the way down to the 5 meters?
Yeah, so I mean, this has just all happened within the past couple days.
Mm-hmm.
So obviously, each step, you can't just like hammer yourself down immediately. There's the diagnosis step where you have to take photos and make sure that it did what you thought it was going to do, and then plan what you're going to tell it to do next, and then they have to test it in the test
Right.
bed before they send the. So it's a very long,
this sort
drawn-out
of
process.
remote space exploration tends to be a very careful,
Yes.
slow,
Yeah.
deliberate
Yeah.
process.
Yeah.
At least in the U.S.
Yeah.
It is still other countries, but like the Japanese Hayabusa mission, they're much more like
They've
rapid
they've
turnaround about it.
Yeah,
it's pretty fun.
cranking along, but
But you don't want it to like something else to go wrong because you didn't test it first or you didn't
Right.
evaluate
Yeah.
what the situation
Yeah.
is.
you
we have
can't
to
make
be-
a house call.
We have to
Yeah.
be very careful with how we use the arm. There's a
Mhm.
lot of risk associated with using the arm, so
Right, don't want to break it.
I don't want to break it.
But you're not involved. Your main science involvement with InSight's not with the mole.
No,
It's with SICE.
it's with the seismometer, the seismic experiment for internal structure.
That's a nice backronym.
What did you call
A
it?
backronym.
Because you
You work
backwards
backwards
from
to
the
make sure you
acronym
get
to
the
make
acronym
up a
you
name.
want.
Yeah.
But it's relevant.
Yeah,
So the seismometer is looking for Marsquakes and
correct.
things like that.
Yes, so you can see Mars quakes.
So Earth has earthquakes because of tectonic plates and things.
Right.
Does Mars have tectonic plates, or
So Mars does not have tectonic plates. Mars is what we call a one-plate planet or a stagnant lid planet.
stagnant lid?
I have not heard that before.
Oh, really?
Yeah.
It's like there's heat underneath.
But it
there's-
can't go anywhere.
There's no,
Right.
like,
Right.
So like most
It's
of the
like
other planets
when
are
That's,
that way.
That's usually also anytime I cook, you end up with a stagnant lid.
Yeah, it's
Anything
true,
I
yeah.
put in a pot ends up with a stagnant lid.
Yeah.
So the tectonic forces are largely related to contraction. So as the planet loses heat, it actually shrinks,
And is that still happening today?
which we think is
4.5
still
billion
happening.
years
today.
after.
Yeah.
Yeah, we think there's still some heat in Mars,
Yep.
so there's still some shrinking.
So
But
there's still
less,
some cool
less
But
than
even, like, on
Earth,
the
right? Because
moon-
it's
Yeah.
smaller.
But even on the moon, there's shrinking that's happening still.
And in fact, there was a paper that recently came out, written by someone that you might know.
Oh, interesting. Was it
showing
you?
showing a link. between tectonic features on the moon and moonquakes recorded by the Apollo experiments.
Fascinating.
So,
But are those? I thought on the moon it was tidally forced, the quakes from tidal
yeah, so there are
stretching and
different
stuff.
types of seismicity on the moon.
Seismicity, nice word.
The deep,
I prefer stagnant lid.
the deep quakes are the ones that are tidally related.
Because the Earth and the Moon are stretching and squeezing each other.
Correct. So the same gravitational interaction between the Moon and the Earth that causes tides in the Earth's ocean also causes what we call solid body tides in reverse on the Moon.
We're getting a lot of cool lingo.
The Moon
Jingos.
doesn't.
Jingo is a combination.
The Moon
of
doesn't
jargon
have
and
an
lingo.
ocean, right?
It doesn't.
So,
It has mare, but not oceans.
in fact, what happens is that the entire planet just deforms.
And the
Except-
same thing does happen to Earth. It's just that it's
so
much
sm-
much
it's
more
much,
obvious
much
that the
smaller.
oceans.
Yeah.
Except I thought with the moon, I mean, the moon is tidally locked to Earth.
Correct.
So is the only
vibrates.
reason for it the fact that it's got an elliptical orbit and it's sometimes closer and sometimes farther, so that
So the strength of the tidal stretching has to vary
changes.
because of that, but also
Right.
because
Vibration.
your azimuthal speed varies, you're not always in
Yeah.
perfect sync. So
Sometimes
that's what leads
slightly
to
lags
vibration.
and sometimes slightly leads.
Right.
But that's all coming
It also
from the
does
eccentric,
this.
the
Mhm.
the
Does
elliptical
latitudinal
orbit.
and longitudinal.
Longitudinal.
I just did it backwards, but anyway, yeah. So Mars.
Check the video for sweet dance moves.
Right.
So on Mars, Mars has moons, but those moons are
They're little
Moons.
babies.
so small.
Yeah.
Moons in
that
quotation.
they
Trash
don't-
moons.
Air quote moons.
They do actually raise a tide on Mars,
What?
Yeah.
and size
This
is
big?
sensitive enough to measure that.
That
Yeah.
Your
amazes
size,
me.
the instrument. I thought you were
Size-
saying size, the word. I thought you were going to say
size
size
instrument.
matters or something. But
It
the
does.
instrument,
Seismology definitely matters. Yes.
so the
Instrument size.
tides raised by the little pipsqueak moons, Phobos and Deimos.
I think just Phobos
Deimos is further
It is
or
further.
smaller.
and smaller.
Yeah.
I think it's
Yeah.
both,
Yeah.
so it's harder. You won't be able
Yeah.
to see that as easily.
So we think that we can see the Phobos tide, or we should be able to eventually constrain the
But you're
Phobos
not sure.
tide.
You haven't yet detected it, or you're
It
not
takes
sure?
a long period of observation.
Okay. So what sorts of things have you seen so far with the seismometer?
So far, with
Wind.
the seismometer, we have seen or heard wind,
yes.
atmospheric pressure variations, also dust devils,
Yeah.
some quakes.
Yeah, so you see the dust devils because it actually causes a pressure difference that actually sort of makes the ground
Yes,
itself
actually
move.
deforms the ground.
That's
That is
crazy.
nuts. I cannot believe it is sense enough to pick all those things up.
Yep.
That's
Yeah.
crazy.
It's so sensitive.
So it can see whatever the lander's doing.
Isn't there some story about when they were testing it, it was like so sensitive that it was picking up like bells at churches nearby or
Yeah,
something?
so that was the SP instrument, which was a contribution from the UK. And they have a lot of churches,
Mm-hmm.
I guess, in the at Imperial College where the
it's testing.
seismometer was being built and tested, and that they could actually see those
Right.
signals on the test data.
Cool.
Yeah.
And so the quakes you've been seeing, those are thermal cooling quakes, sort of.
So-
that's the shrinking of the planet.
Yeah, so we
in
think
little
they're
bursts and bits.
possibly tectonic in origin, but it's kind of too soon to tell.
Okay.
Yeah, those analyses are still underway.
Okay.
Yeah.
What else could they be?
What else could the signals
Aliens.
be that we see?
Always. Okay, that's always a possibility.
So we think.
Oh, NASA's never going to let this go out.
So we think, yeah, there could be a variety of different things happening, right? In addition to sort of what we would think of like a large tectonic earthquake, or maybe like a thermal quake, something that you would see because of shifting regolith, or actual like thermal expansion and contraction. There could be meteorite impacts,
Right.
right, that we're detecting, because a lot of that stuff that would burn up in Earth's atmosphere makes it through Mars's much thinner atmosphere.
Right.
And in fact, we have before and after images taken from orbit of freshly formed impact craters.
Cool. And have you been able to correlate those yet, or is
Not
that
yet.
something that you're
Yeah,
looking
we're
to
still
do?
working
maybe
on
do?
that.
So you can like maybe go back and actually see this
Right.
signal in the seismometer
Right.
data correlates with this particular impact.
So we get the seismic data down much faster than we get the image data,
Uh-huh.
because the image data, you can only re-image the same region every so often because it just depends on the orbit of the spacecraft
Right.
of the Mars
But
reconnaissance
that would be
orbiter.
really exciting because then with the picture of a crater, from just looking at the crater, you'll know something about how much energy was delivered, and you know exactly where that energy
Where it
was
was,
delivered.
when it was.
And then you see
yep.
the seismic signal, that'll
Mhm.
tell you, I imagine,
Right.
quite a lot about what the interior, because that's how we know a lot about the interior of the Earth, right, is by looking at seismometer data from earthquakes
Yep.
and catching that data all over the world
Yep.
and seeing how those waves travel through the interior of the planet.
And in fact, I think yesterday was the anniversary of the big Loma Prieta earthquake in California.
Mm.
I don't remember exactly what year that was, 89 maybe, which is just like the really huge kind of event that's picked up by instruments all over the planet,
Right.
Ooh.
which is something that we would love to see on Mars.
Yeah. Soon, someday, maybe you'll have seismometers all over Mars. The moon first, though,
Yeah,
right?
both.
Moon first.
Both.
Mars.
Both.
Okay. Now, before we move out of the
Seismometer all the planets.
Yes.
What about Jupiter?
Well, it's
Maybe.
Why
it's
not?
giant. It's a little harder.
It's a little hard.
You can do helioseismicity, so
That's
Yeah.
true.
or
That's true.
helioseismology.
Yeah. We talked about that recently with Kepler data.
Before we move out of the solar system, I'll drop the trivia on you. As it's frequently the case these days, it's multi-part trivia. Do not blurt out your answers because
Okay.
we will
Just
come
think
back
about
to
them.
those at the end. This is just so that in your background you can be processing
I
and coming
definitely
up
do
with the right
that.
answers. So we've been talking about...
Wait, do I
state-
get to write my answer
No.
down or something?
No.
No.
We just gotta
To
keep
hold
have
it
to
in my
hold
head?
everything in your
Brain, I
head.
know.
How many questions are there?
There's like 6.
Jeez. Probably 2. Are there really 6?
I don't know. There's
Gosh.
there's one main question.
All right, let's go. Let's get going.
All right.
Okay, this is about all those huge numbers of satellites we were talking about,
Great.
right? So, according
Saturn.
to the United Nations Office for Outer Space Affairs, which would be an awesome place to work just because of the name. I don't know what it's like to work there, but United
Okay,
Nations Office.
when we're done with the trivia, remind me to show you my desktop picture on my laptop.
Okay.
Okay.
Can we share it on our Facebook page or our website?
Sure.
Okay.
Great.
According to the United Nations Office for Outer Space Affairs, how many objects have been launched into space, period?
Are outer
Oh
space
my
affairs when you're like dating one alien, but
I
then
know,
you cheat
that's
on
why
the
I know, that's why
How
it's
many
such a cool...
objects just
I've-
launched into space?
Period.
total?
Yes, and this is not including suborbital. Okay, so up and down, not counting that, but launched into space
Poor
and left
Does
in
this
space.
does this count like if you launch a thing up there and then like 20 things come out of it?
Yeah,
does
does
that
is that
count as?
1 or 20?
Oh.
That is 20,
Oh.
Okay.
if it's a
okay.
planned deployment. Now, if you launch it and it breaks apart,
Right, right. No,
that,
no, yeah.
you don't
Okay.
count all those
Right.
bits
Like
and
if you
pieces.
have
But like all
20
these little
CubeSats that are
CubeSat
gonna
things,
get
yeah.
That's 20,
Squirted out of the
Okay.
ISS.
That's 20.
Okay.
right. So, the 60 Starlink
Wait,
satellites...
wait. Follow up
were-
question. Each individual like piece of the ISS count as a separate item? Because they weren't all launched at the same
But
time.
they were assembled.
Yeah.
No,
No.
Okay.
I don't know, honestly, but
Maybe
I'm
ISS
going to
stuff.
just say
Does like
no.
shuttle stuff count then?
We're way too
Or is
nerdy
the- or
for
this
this
is
trivia
just satellites.
question.
This is just satellites. This is just
No,
satellites.
you just said anything launched into space.
Launched into space.
All right.
Launched into
Since
space.
Is this
forever?
going to be a multiple choice, or are we just going to have to guess?
To-
It is
to what-
multiple choice.
To what
Okay.
to what
And
level
your-
of
choice.
precision?
It's multiple choice,
Oh,
and
okay.
your choices are all positive
Ah,
integers.
damn you. Damn you
All
into
positive
tricking me
integers
into believing.
Between
1
10
and
1
million.
billion. Okay.
Okay.
So you have a million choices.
Okay.
That's going to be
Would
a
you
hard.
like to hear them again?
No.
Wait. I thought you said it was multiple
Yeah, he
choice.
was
It is.
It is
1,
one,
2,
two.
3, 4, up to a million.
Oh.
Those are your
That's
choices.
why I said damn him. Yeah. So
Okay.
maybe I heard to bubble in on a Scantron.
Yes.
All right.
All right.
All of the other questions are just derivatives of that one.
So is it
All
like
of your questions are derivatives.
whoever
Josh.
gets closest
Yeah.
is the winner? Is that
yeah.
the deal?
Oh,
Yep.
yes.
Okay.
And
Yeah.
it is not Price is Right rules.
No, we've gone off on Price is Right rules
You
before.
wanted Price is
I
Right
was gonna say a
rules?
million.
Nice job. That would be a good guess.
Yeah.
Okay.
Okay.
So,
Okay, back to our regularly scheduled programming.
yes.
What are we
Alright.
talking about next?
I don't know. What are we talking about next?
Your thing.
My thing.
Yeah.
Oh, we were going to talk about cuspy halos.
Cuspy?
That sounds so fun.
Cuspy halos.
Cuspy,
halos.
C-U-S-P-Y?
That's right.
Halos?
Is that? I don't even know if that's a real word, but that's the word we use.
Do we use it?
We use it in astrophysics.
Do we really?
Yeah.
Yeah.
I've
Cuspy.
never used that word.
Really? Well, you need to get
So
more heavily
halos-
involved in the large-scale structure of the universe community.
Halos referring to the halos of galaxies?
Halos of galaxies, right?
Okay, so those are not really very well observed, but known to exist dark matter,
Right.
spherical
And there's songs about them.
distributions of dark matter.
Sounds
Yes.
like a Nick Drake
So,
song.
so that's
Halo?
Yeah.
Is that Beyonce?
I don't know.
the dark matter idea comes from seeing things swirling around too fast, and they say there must be a lot of mass there that we don't see. And
Right.
a spherical blob around the galaxy, that's the halo.
Right, that's the halo.
So what's
Mhm.
a cuspy halo?
A cuspy halo is... So when we are modeling what the dark matter should be doing, we use things called n-body simulations, right? We
N-body simulation
N-body
should sponsor
simulation.
the show.
They
should.
should,
They'd
because
be a
we've
great
talked about them a
sponsor.
few times. Yeah, we just run computer simulations. We plug in all of the appropriate physics, gravity, and all of the other things that are going on, and we let the thing run to see how does dark matter arrange itself if you give it a long time to arrange
It's very
itself.
simple.
You put n bodies in your computer program, where
Yeah.
n is a very big number.
And it's a very big number, and
And
each
you-
little
and you
body
say
represents
go.
a little bit of dark
Between
matter,
one-
and you say go, and you see what
they
happens.
go.
And they go. And we run these simulations, and what we find in the simulations is that dark matter knots up into places where, like a galaxy would form, but that the density of the dark matter increases the further in towards the center of this knot that you get, and it increases all the way until you get to the very middle of it.
Well, that sounds sort of what you would expect, isn't
Except not
From
really.
the
What
way
we
matter behaves.
what we actually see is these halos seem to increase in density until you get to a certain point, and then it levels off.
it? Oh.
Mm.
And so the question is there
as you
this
get
cusp
closer,
or isn't there?
As you get closer and closer towards the center, the density stops increasing.
Right. There's at some point it plateaus
So
and
it's
is
like
fairly
it's
uniform.
increasing, and then it stops increasing. That's the cusp. Those
Right.
little corners
Right.
there,
Mhm.
instead of going up in a nice smooth curve.
Right.
It's like a hat. or a
Right. So
mesa.
so we've had this kind of
Is it extra tasty cuspy?
I don't know. I don't know if you have to pay extra for that or not.
Oh.
But this has been a giant problem for us in that the simulations don't match the kind of other theoretical things that we're doing. So the question is,
the simulations produce the cusp.
the simulations seem to indicate that
It should
It
be.
should
it
just
should
keep going
continue
up.
to go
But
up.
the observations seem to show that they don't.
Right.
Some simulations
Hmm.
predict cuspy halos.
But in the kind of in the wrong way. Basically, what's happening is our
They
n-body
cheated.
simulations are not handling the small scale structure of this stuff very well. They do a really great job of predicting the behavior of stuff on very big scales, and that's been one of the really great. That's one of the reasons, for example, that Jim Peebles, we mentioned last episode, won the Nobel Prize in physics for his work on understanding this stuff on the large scale. It works ridiculously well in predicting the structure of the universe on the large scales. But when you get to small scales, it doesn't work very well. It's not terribly surprising that it doesn't, because all of
Well,
our...
the bodies that are in the n-body simulation are big bodies, probably.
They're big bodies, but they're, I don't know. All of our kind of analytical framework for all of this works really well for big structures and not for small, because in small structures the density is very high, and when density is very high, it's not well described by our stuff.
Well,
Anyway, that's not a good explanation.
Well,
but
the computer, if you wanted to really simulate every single thing in there, you'd need a computer program where n is like the number of atoms in the whole galaxy.
Right,
you can't
exactly.
do that.
You can't do that, right.
Right.
So, yeah, it's very hard to simulate both the large-scale structure and small-scale structures, and we try and do that by, like running the large-scale structure and then zooming in and running a new simulation on those
Right.
smaller scales and stuff. But anyway, there's always been this problem. And,
So what's
the recent news seems to be, and we've been worried about this in cosmology
have
for the
been
past.
worried.
It's been keeping you up
Have
at
you guys?
night.
I
It
have
actually
not.
has been keeping me up. This was part of something that I worked
so-
on for my PhD thesis was an attempted solution to what's going on with the cuspy halo problem.
So many things keep you up at night.
I do not sleep well.
The list of things.
I
it's
did-
in-
I know.
And
Just
somewhere
like
on,
the universe ever expanding.
somewhere on the list is cuspy
Cuspy
halos.
halo. It's a serious for people in the large scale structure of the universe, people in cosmology. This has been a serious problem for the last decades.
Okay.
But it might
What's the
just be.
answer?
The thing is, this recent paper suggests it might just be.
Somebody forgot to
Basically-
carry the 3.
No, yeah, it's like an artifact of the computer code that we're using. So that is,
It's always a bug.
It's a
somewhere.
rounding error.
it's not a bug so much, but it's just like it's like the way we do the calculation will always produce this weird error, and we've never thought to go back and change the way we do the calculation. It's not the physics that's wrong, it's the specific computer code that we're using.
And even though different people use different codes to do it,
But they all use that same technique
Yeah.
in this inner part of this halo, and that technique is producing an artifact.
What is this technique?
Well, that's
I
beyond.
must know.
You know,
I
it's
must know.
beyond the scale. It's
This
very
is-
very complicated. I mean, this computer code is millions of lines long, and so it's reasonable that when you make new versions of it, you don't like write it all from scratch every single time, and so we end up using like the original version that has this artifact
Because
in
it
it
seems to work.
because it seems to work, and it works
for
for
a lot
everything
of
else
things.
except in that little cuspy halo part.
Okay.
And so it may be, we're not entirely sure this is true yet, but the argument is being made, look, it's
So that means
it's
you
this.
should be able to trace it back to one single individual that wrote that
Some-
one
somebody-
code.
Oh,
That's
I don't
right.
want to be that. I
Is
hope
it
it's
gonna
not
be-
Jim
is it
Peebles.
Jim
The guy who just
Peebles?
won.
No.
Probably not. I don't think he was
No.
involved. But
Well, I was going to say maybe it was you, and that's why you're losing sleep over
it certainly it was not me. I'm
We-
not smart
we
enough for
know
that.
Jim wasn't the one writing the
So
computer
this
code,
is
Josh.
why scientists are notoriously bad at commenting their code, because they don't want anybody to know that the bug was their fault.
Yeah,
So-
yeah. No, perhaps if this code had been better commented in the beginning, this wouldn't have happened. So
happen.
we're not positive this is a
assumption
solution.
is maybe not the best.
but-
Don't
But yeah,
continue with it.
the moral of the story
Bougie
is
stuff here.
code your stuff well and always check whether weird things are happening.
That's
So
the
are
moral
there
of the
some
story.
so I guess this new paper, right, did some analytical approximations that differently to say, okay, maybe this is how you get this overshoot, right? So
Right.
there are other ways to do it, and maybe we can try
And-
those.
and
Right,
So
so-
there's not only there's some indication that you get around the cuspy halo problem if you do this calculation a different way.
Right.
Okay.
So somebody's going to have
So
to
then-
invest the time and
You
effort
can
in
get sleep
writing
now.
a new,
Right.
write some new
It-
computer code that avoids this thing, and maybe I can sleep.
You'll sleep
But there are
like
so
a
many
baby.
other reasons I can't sleep. It doesn't matter.
This is the most important one. I'm really feeling good about your future here. Our last item was about a cool thing of white dwarfs that have eaten up their planets. It's this weird thing where
More of these dwarfs, not dwarves, also.
we can say either, we learned.
That's true.
Yeah.
We can do it either way we'd like. So a white dwarf is the leftover ember of a star. So like the sun will someday become a white dwarf, and it's got planets around it. And if it doesn't burn up all the planets around it, after it's a white dwarf, it'll still have some planets, and those things can spiral in and crash onto the surface of the white dwarf.
That
So
wouldn't be the worst way to go.
What's
Yeah.
the surface
No,
of a
but-
white dwarf like?
Death by white
Very, very hot.
dwarf. Yeah.
well,
And
initially
crushing
Initially.
gravity.
crushing
Mm.
gravity.
Crushing
So
gravity, they're
what's
very
what's a white
dense.
dwarf like? It's about how big?
It's smaller than the sun.
White dwarfs are about
About
planet
the-
size.
about-
Bigger than
Yeah.
a bigger than a bread box.
Yeah.
yeah,
It's
they're
about,
bigger
it's
than
about
Planet-sized.
Earth-sized,
yeah,
roughly,
they're about
right?
Earth-sized.
But with
But they
about the
have-
mass of the sun.
Right, and that leads to surface gravity, something like 100,000 times greater than Earth's surface gravity,
Right,
and
still-
the temperatures are crazy high.
Piddling compared to a neutron star in
Right, this
terms
is
of gravity.
nothing compared to that, but
It's still
still
crushing.
enough to kill you.
Right.
That's
So
for
if
sure.
another planet came and had a close encounter with one of these, would it break up before it actually impacted?
It would probably be
Certainly.
tidally disrupted.
Certainly,
Yeah.
and I think that's part of the point of
That-
this, right?
that's
is that
part of what happened
it
here.
breaks apart, and then
And
you
you're-
look at the spectrum of light coming from the white dwarf, and you can actually tell what the interior of that planet was made of
Mhm.
because
These
it's been
additional
broken
Because
apart.
it's been smeared all over the place. So
That's
the,
an interesting way to get at the interior of a planet.
of
Yeah.
exoplanets,
Yeah.
right?
Mhm.
So the
Mhm.
white dwarf itself is sort of like looking
Not
at
recommended.
the naked core of a star.
Right.
And so it's mostly carbon.
Mhm.
Yeah.
And so it has a very simple spectrum, but some white dwarfs, we look at the spectrum and we see that there are these silicates and other spectral
Metals, yeah.
signatures that presumably came from planets that crashed on them. So in this latest paper, the oxygen fugacities of extrasolar rocks.
I do like the word fugacity.
Sexy title.
Fugacity is a
Fugacity.
good
Fugacity, yeah.
word.
That's
I'm
I
still,
think that's a band also.
still going with stagnant lid.
The fugacities.
They were able to measure on 6 white dwarf systems that the composition of the elements left by crashing planets had the same oxygen fugacity, which is sort of a measure of how oxidizing or not that the environment that rock formed in was. So some chemical measure of what the rock's environment was like was very similar to those of Earth and Mars. So that's
Interesting.
pretty interesting because I've been harping. One of my favorite things to harp on, and I have so many.
You also don't sleep well.
The list of things that Jim stays up at night over is equal to the list of things that I get harping about.
Get worked up about?
Worked up about, thank you.
You're welcome.
And one of them is how we have not really been very successful in finding other planetary systems that look like our own. But here's a nice observation in maybe the least likely of places that shows evidence that there are planetary systems, or there were planetary systems that formed like our own, with terrestrial planets where the rocks formed in the same sort of environment that the rocks that the Earth and Mars formed from.
Mm-hmm.
Right on.
So that's kind of cool. Polluted white dwarfs.
Yeah.
Yeah. All right, you've had a few minutes to
I've
ponder
been-
your million
I've been
options on the trivia.
Mm.
How many things have been launched into space?
I think guests first.
Oh.
Okay. Well, I recently looked up how many people have ever been to space
Mhm.
because I was going to space camp to talk to
Nice.
a bunch of space campers.
What's the answer? Can we guess on that one?
Sure, yeah.
We can turn that into a
How many
reverse
people
trivia.
Reverse
have been launched
trivia.
into
How many
space?
people? I don't remember the exact number, but I remember ballpark.
I'm going to say 400.
It was more than that.
More than that?
Yeah.
Have been launched into space?
Yeah.
That's surprising. 700.
Less than that.
563.
So Addie's closest.
Well,
It was
sure.
500 something.
I said 400. You said more.
Yeah.
He said
So-
700. You said less.
I'm gonna use that-
because when Beth Moses got hers,
That's a
it was
setup.
like how first.
Okay, so
okay,
you know.
so I'm going to use that to extrapolate.
Okay.
So if I say that for every person that's been into space,
Mhm.
there have been at least 100 inanimate objects launched into space.
Okay, it's reasonable.
I'm going to say 100 times 500.
Okay.
50,000.
There you go.
I am gonna. So there's been something on the order of like thousands of CubeSats just in the recent years, right?
Don't say right. You don't get to. He's not giving you any hints.
I'm gonna go. You went with 50,000.
Yeah.
I'm gonna go with 42,000.
I'm going to go lower. I'm going to go
Oh.
with.
I think it might be higher.
Absolutely. It could be higher. I have no clue. I'm going to go with 17,560.
Oh,
Ooh,
nice.
okay.
So, as you'll recall, my question was phrased, how many have been launched in space according to the United Nations Office for Outer Space Affairs?
Uh-huh.
That absolves me of any responsibility for inaccuracies in this number.
Great.
Okay.
And I'll tell you after I give you the answer that they have how my one validation of interpretation of the number. So their number is 8,761.
Whoa.
Nice.
And
That's so low.
I did a
That's really
search on suborbital things that I know have gone up and they were not found. And I did a search on SurfSat,
Oh yeah.
which is a satellite that was launched as a secondary payload
Mhm.
developed by Charm Astrocorp Addie Dove
That's
here
right.
and launched a year ago
Yeah.
on a single rocket, but as one
But
of
with-
maybe
were
10 total payloads
No,
or
there
something.
are only 4.
Four total
CubeSat-
payloads.
or-
4 CubeSats and a
and the
primary
primary
payload. So
payload.
5 things. SurfSat was individually on that list as an individual thing, which suggests that it does count,
Secondary
even though it was a
payloads.
single launch, those
Mhm.
things separately. So that's that. Your international designator, by the way, do you know what it is for SurfSat? It's 2018 070B.
Yes.
Because
Because 070 A, B, C, and D are the cube. Or A is ISAT, and then B, C,
B,
D
and
are
B.
the CubeSats.
Okay.
Hmm.
So that's why I think that it counts everything that was like deployed, if even though it was
Mhm.
single launch. 8,761.
Wow.
Your derivative questions were
That's so few.
how many are there that were in orbit still around the Earth at the start of this year, 2019? So it's not less
In
than
orbit
that.
and communicating, or
No.
just in
Mm,
orbit?
just
in orbit.
Okay.
In orbit around the Earth.
So how much space junk is there? I guess?
5,000.
That's so close. I'm not even going to let the others guess.
That's what I was
Okay,
going to guess
great.
too. God.
4,987.
Wow.
Okay.
Nice.
Yeah.
And
Including
13.
SurfSat, Murph.
That's right. That includes SurfSat. The biggest launch year so far was 2017.
Yeah.
Care to guess how many were launched?
How many individual launches were in 2017?
Not launches,
spacecraft.
objects.
Objects.
So Addie's launch was one launch, 4 or 5 objects.
I don't know.
640.
I'm going to say 365.
117.
453. I think Renee gets that one.
Nice.
Yeah. And the number that are functioning of those 5,000 is about 1,900.
Okay.
That's more than
Give
one
or
thing
take.
launched per day in 2017.
Yeah.
That's
That's right.
nuts.
That's crazy.
That's right.
Wait,
so
what
we'll
was
s-
it? 300 and
Four-
400 something. Yeah, yeah.
Wow.
453 objects per day.
And that's because
We
that
looked
was
at-
because 2017 saw a lot of CubeSats finally get launched
Yeah.
too.
And
And those are a
we
lot of
looked
like
at-
secondary payloads.
We looked at launch numbers, and I think the biggest launch year was under 200, but it was up over 100 launches in 1 year.
That's
Wow.
what I was thinking of is number
Like
of
just
launches.
number
Number
of
of launches.
actual
Yeah.
rockets
Yeah.
with flames coming out the back.
Yes. Oh man, did you see the Ohio State marching band
No.
performance? Yeah, you did the Apollo
Oh,
marching
yeah,
band
yeah, yeah.
performance.
Yeah, yeah.
And they had like
Oh.
a fake rocket launch, but they had like fire
Like little,
extinguishers
like,
that created rocket
Smoke
plumes.
Oh,
plumes
cool.
coming
It
out
was
the
so
bottom,
amazing.
and then they had like on-field pyrotechnics.
Yeah,
it was
it was
really
pretty
cool.
amazing.
We'll put a link. While it may have felt like the time for a white dwarf to cool off, it was just another episode of Walkabout the Galaxy. If you like this episode of Walkabout the Galaxy, write us a review in Morse code and play it subsonically so that it propagates through the Earth and is picked up by seismographs around the world.
Ooh.
If you didn't,
Don't,
well, there's
don't
no...
do that.
Don't do that?
That's not a
Yeah.
good idea.
That's a good idea. If you didn't, well, there's no accounting for taste. Be sure to like us on Facebook to get all our updates and check out our website at walkaboutthegalaxy.com. Get bonus AstroCorp goodness on the Are We There Yet podcast from WMFE 90.7 space reporter Brendan Byrne. Subscribe to our YouTube channel, Walkabout the Galaxy, where you can see Addie and Renee doing whatever dance you were doing earlier. What was
A
that?
little
Vibration
vibration
dance.
dance.
Vibration dance, where you can see Addie and Renee do the
Oh,
vibration.
and the mole.
And the mole
Shimmy.
The mole
Yeah,
shimmy.
The mole shimmy.
Vibration Dance and the Mole Shimmy. Catch up on old episodes wherever you get your podcasts. Thanks to our listeners in Alberta, Canada, and around the world. Follow us on Twitter
At walk_that_galaxy.
and ask us questions anywhere using hashtag WalkaboutTheGalaxy. Our theme music was composed by Richard Jerusik. Our production assistant and video guru is Diego Rodriguez. Thanks again to NASA's Dr. Renee Weber for joining us today. I'm
Pleasure to
Josh
be here.
Caldwell.
I'm Addie Dove.
I'm Jim Cooney.
We're the AstroQuarks signing off until the next episode of Walkabout the Galaxy.
I don't know.